So today we're going to look at matrix transformations. Matrices can represent transformations in 2D or 3D space. So let's take we take a point x, y. If we multiply that by say 2, 0, 0, 2, we would get 2 times x plus 0 times y. That would give me 2x. And we would get 0 times x plus 2 times y, which gives me 2y. So we've ended up with a new matrix 2x, 2y. We've transformed the original matrix xy into this new matrix 2x, 2y. In other words, it's been multiplied. It's been scaled by a factor of 2. Okay, an enlargement by a scale factor 2 about the origin, or in advanced higher maths, we'll call that dilation. Okay, let's look at some other transformations. So if we look at this example, what transformation does the matrix 0, 1, minus 1, 0 represent? Well, if we just times 0, 1, minus 1, 0 by a random point xy, it will tell us what we get out, and we can work out the transformation. So 0 times x is 0x, 1 times y is y, minus 1 times x is minus x, 0 times y is 0y, so we get y minus x. Now we can see what's happened by plotting a random point xy. So if I plotted a point, say 3, 1, well, that ends up becoming, the y becomes 1 on the top, and the 3 goes to minus 3, so we can see that this is a rotation 90 degrees. Sometimes hard to see exactly what the transformation is, but there's easier ways to check later on. So let's look at, in general, transformations. If we take a point, we can turn that point xy into the vector xy, it's a position vector. And if we transform it in some way, the new point is called the image. And we denote that x prime, y prime. X prime, y prime, the image, all you need to do is take some random 2 by 2 matrix, A, B, C, D, and times it by xy. So A, B, C, D is called the transformation matrix, xy is your point, x prime, y prime is your image. Let's look at some standard transformations. Reflection on the x-axis. If we take a point xy and reflect it over the x-axis, well, x stays the same, but y becomes minus y. We just take our image, x prime, y prime, equals, well, that is, if I look at our image, we've got 1x plus 0y on the top, and on the bottom, we've got 0x minus 1y. And taking that out in the standard way, our coefficients of x and y, we would get 1, 0, 0 minus 1 times x, y. So our transformation matrix, of course, is 1, 0, 0 minus 1. There's our transformation matrix for reflection in the x-axis. So reflection in the y-axis, x goes over, becomes minus x, but y stays the same, it stays the same height. So x prime, y prime, our image, has become minus 1x plus 0y and 0x plus 1y. Taking our coefficients of x and y, we get minus 1, 0, 0, 1 times xy, and therefore minus 1, 0, 0, 1 is the transformation matrix for reflection in the y-axis. So if we look at the line y equals x, if we take a point xy and we reflect it over this line, then all that happens is that x becomes y and y becomes x. So starting with our end point, our image, yx just equals, well, 0x on the top plus 1y and 1x on the bottom plus 0y. So that equals 0, 1, 1, 0 times xy. 0, 1, 1, 0 is the transformation matrix for reflection in the line y equals x. Moving on to some rotations. Rotation pi radians about the origin. So if we take a point xy and just rotate it 180 degrees, pi radians, then x becomes minus x and y becomes minus y. Let's look then at what that transformation matrix would be. So we've got minus x minus y Should be getting the hang of this now. We've got minus 1x plus 0y, and we've got 0x on the bottom, minus 1y. So our transformation matrix pops out as minus 1, 0, 0, minus 1, x, y. So the transformation matrix for rotation pi radians about the origin is minus 1, 0, 0, minus 1. Now, if we're going to talk about any other rotation, we have to define a direction, because for 180 degrees, it doesn't matter what direction you go in, but for any other, if I say pi over 2 radians, in other words 90 degrees, am I talking about going this way anti-clockwise or this way clockwise? For the purposes of this, we will mostly define them, or always actually, as anti-clockwise. So, rotation of pi 2 over 2 radians, anti-clockwise about the origin. So if we take our point and we go 90 degrees this way, then x becomes minus x, but y stays the same. So we can work out our transformation matrix. Minus xy has equals minus 1x plus 0y, and 0x plus 1y. So that equals our transformation matrix minus 1, 0, 0, 1 times xy. So our transformation matrix for pi over 2 radians anti-clockwise rotation about the origin is minus 1, 0, 0, 1. Now I'm not going to prove this one in this video, but I may do a further video in the future, but it can be shown that a rotation of theta radians anti-clockwise about the origin is given by this transformation matrix. So by theta radians, I mean starting with a point, moving theta radians this way to give our image. Your transformation matrix will be cos theta minus sine theta, and cos theta. This transformation matrix is given to you in the advanced higher exam. So you do not have to remember it, you just need to know how to use it. Dilation. So dilation is scaling. So let's say we've scaled the point x, y by a factor of 6 in the x direction and 6 in the y direction, and we've got a new image which would be 6x, 6y. Well, our transformation matrix for that would be, well, we've got 6x, 6y as our end image. So that equals 6x plus 0y. And 0x plus 6y, so we've got 6006 times xy. So you can see here that 6006 would be the transformation matrix for a scaling of 6 in the x and y direction. In fact, in general, a dilation of a factor of k is given by x prime, y prime, our image being k0, 0k times xy, where k0, 0k is our transformation matrix. Now obviously we could have independent scaling where we times the x by some number and the y by some other number. If that was the case, our image would just be a0, 0b, xy, but a does not equal to b in that case. So basic transformation matrices, reflections. Reflection on the x-axis is given by 1, 0, 0, minus 1, and in the y-axis by minus 1, 0, 0, 1, and in the reflection in the line y equals x is given by 0, 1, 1, 0. You can memorize and just remember these, or you can, probably better, to try and actually work these out yourself at the time using the method that I've just given you. So a rotation of theta radians anti-clockwise about the origin, this is given in an exam, is given by cos theta minus sine theta, cos theta. You can obviously work in degrees if you prefer. A rotation of pi radians about the origin is given by minus 1, 0, 0, minus 1. You could get that yourself just by substituting pi into here, or 180 degrees. And our last one, dilation, scaling. If we've got a dilation factor of k, then the transformation matrix is just k0, 0k. Obviously, independent scaling, where we can have a0, 0b, where a does not equal to b. Let's look at some examples. So write down the 2 by 2 matrix associated with an anticlockwise rotation of pi radians about the origin. So we can just write that down straight away. It is minus 1, 0, 0, minus 1. Part B. Hence, find the image of point x, y under this rotation. So remember, our image is just x prime, y prime, and that equals our transformation matrix times xy. So that equals minus 1 times x is minus x, 0y, 0x minus y. So minus x minus y. So our point, to be clear, is just equal to minus x minus y. Find where the matrix 5, minus 2, minus 1, 3 maps the point minus 3, 1. We have got our image x prime y prime equals our transformation matrix times our original point as a matrix minus 3, 1. So multiplying that together, we have got 5 times minus 3 on the top, minus 2 times 1, and then we've got minus 1 times minus 3, plus 3 times 1. Tidying that up, we have got minus 15 take away 2 is minus 17. And on the bottom, we've got 3 plus 3, which is 6. So our point becomes minus 17, 6. Write down the 2 by 2 matrix associated with an anticlockwise rotation of pi over 2 radians about the origin. And then for part B, find the image of point P under this rotation. So let's start with A. Pi over 2, so M, remember, from the exam sheet is cos theta minus sine theta cos theta. So we can substitute pi over 2 in. Cos pi over 2 minus sine pi over 2, sine pi over 2, and cos pi over 2. So that equals, well, we're thinking in degrees, that's 90 degrees. So the cos of 90 is 0. The cos sine of 90 is 1, so that's minus 1, 1, and 0 again. And we're done. Now you could have just got that down if you had just memorised it, but there's a way to get it from scratch. Let's do part B. So part B, our image equals our transformation matrix times our point. So that gives us minus y, x. So our image point is just minus y, x. Write down the 2 by 2 matrix associated with a 30-degree rotation clockwise about the origin. Clockwise, trying to trick us. Remember, our standard transformation matrix is defined as cos theta minus sine theta cos theta, but that is defined anti-clockwise. But that's not an issue, so if we take a picture of our point, if our point is going to go 30 degrees clockwise, it's the same as going anti-clockwise by 330 degrees. So we'll use 330 as our theta. So that equals cos 330 minus sine 330, sine 330, and cos 330. So we need to work out the answers to them. So if we get a little cast diagram up, just very quickly, 330 degrees is obviously in the fourth quadrant. So our associated angle, 360 minus 330 is equal to 30 degrees. So if we work out the sine of 30, which is an exact value, that's just a half. And the cos of 30 is also an exact value. That's root 3 over 2. Then our transformation matrix, the cos of 330 is just going to be root 3 over 2. The sine of 330, well, the sine is negative in the fourth quadrant, so it's going to be minus a half. So that's minus a half, which is just a half. The sine of 330 is going to be minus a half volt, and the cos of 330 is root 3 over 2. So our transformation matrix associated with clockwise 30 degrees about the origin is just this transformation matrix. We could take out a half as a common factor if we wanted to, but it's fine like that. Find the dilation matrix associated with a transformation of points A68, B minus 2, 12, minus 12 to A prime 15, 20 and B prime minus 5, minus 30. Okay, let's set this up with, let's start off with our image. So our image, taking A prime as a matrix, we've got 15, 20, and within the same matrix we can do this, B prime is minus 5, minus 30. So there's our image. That equals our transformation matrix times our original points. Our points are 6, 8, minus 2, minus 12. So we've got 15 minus 5, 20 minus 30 equals, let's multiply these matrices together, we get 6k minus 2k, 8k minus 12k. So equating the individual elements, 15 will equal 6k, minus 5 will equal minus 2k, 20 will equal 8k, and minus 30 will equal minus 12k. So just picking one of them. Let's pick 6k. 6k equals 15, and that implies that k is 15 over 6, which equals 5 over 2. We could do a quick check to make sure that that works for all of them. So let's just do a quick check that 5 over 2 is actually what k is. Minus 2 times 5 over 2 is just minus 5, that's fine. 8 times 5 over 2, 8 5s is 40, divided by 2 is 20, excellent. Minus 12 times 5 over 2, that's minus 6 times 5 is minus 30. So 5 over 2 is working for all of the elements, so we now know that k is definitely 5 over 2. And therefore our transformation matrix M just equals 5 over 2, 0, 0, 5 over 2. This has been Claire Mastery. We looked at some basic matrix transformations. Take care, stay safe, and goodbye.